All right. Now, why do we need adaptive traffic sensing or adaptive traffic control rather? It's because the best controls, okay, on vehicle movement can be implemented if you use the information uh, in real time. In real time, okay. So you see the road, the intersection where the vehicles are coming and flocking, right? And look at how far the equivalent is, okay, and what are the different types of vehicles, and then combine all this information together and figure out how much time you should give to each and every lane, okay. So there is an optimal assignment of timing, optimal one. So any other timing adjustment would be suboptimal, okay. So this is optimal control problem, in other words. But in traffic engineering domain, they don't call it optimum control, even though it is really a classical optimal control problem. So they call it adaptive traffic control and try to improve the throughput and all. But if you look at the other side, in engineering, controls and robotics, there's a particular area called adaptive controls, optimal controls and all that. So I'm basically coming from that area. So that's why I'm not originally a traffic engineering person, okay? But I can see the problem, and it's certainly an optimal control problem, and it can be modeled, it can be optimized. So my talk will be aligned in that direction, okay? Right. So our major problem is, let's talk about the major problem here, right? The traffic lights in Sri Lanka or many parts of the world um, work on preset static timing. Okay, preset static timing. So what is the green time? What is the amber time? What is the red time along a certain direction is pretty much uh, pre-programmed onto the traffic light controller, which is a programmable logic controller, PLC. Okay, and it is a blind thing. It doesn't know what is happening on the road, and we assume that based on past data, how many vehicles were there on the road from 6 to 7, 7 to 8, 8 to 9 in the morning, right? Or if you can make it very complicated, what about Saturday 6 to 7? What about Monday 6 to 7? Significant difference, okay? So you can add that also to the table and prepare, right? 7 days a week schedule, right? Every hour, you know how to assign green time for each lane. Or you can make it much more comprehensive, include one whole month, okay, and include every day in a year, 365 days. Then you know Christmas Day is different from other days, okay? Saturday is different from Monday, right? And Poya Day is different from any other day. So like that, you can make it incrementally more realistic, right? And you can assume, okay, fine, this should work. In fact, it works to some extent, right? Um, just because it is not perfect, we should not criticize it too much because it is what is happening all over the world, most parts of the world, okay? Adaptive traffic control or vision-based is still a new thing, right, to the world. But the thing is how much effort you have to put it in there. If you say Monday, this Monday and next Monday, do you get the same traffic? Well, yes, to some extent, but sometimes there are differences. What about there's a road construction somewhere, and all of a sudden your timing is not appropriate, right? And if it is raining, right, in the morning 6 to 7, your timing is different, right? When it is not raining, so these are a lot of factors right, behind that fact, how many vehicles are there on the road on a certain lane at a given moment of time. So it is very, very difficult to model. Okay, you can think about the day, the time of the day, right, and any other influencing factors like rain, etc., and say seasonal changes, Poya days, Christmas, New Year, like that. So there's no end to that one, that these factors. And even though you factor in all these things, right? Think about weather, rain, and all that, and you cannot predict, right? Then you need to have some sort of weather data incorporated to traffic signaling, right? Yeah, of course, you can do that. This is what the modern world is trying to do, trying to bring a whole lot of data, like the goat sees everything, right? You're trying to use sensors and networks and collect all the data available to you, and then you can figure out the situation. Okay, it can be traffic control, it can be something else. So that is where the world is trending, right? So we call it data science, big data, everything, right? So then you find it's not really important to write mathematical equations, because when you have data, you can take the decisions, right? Yeah. So now you understand how bad of an idea it is to use static preset timing, right? But you will be surprised to see, even though this seemingly very bad idea of using preset static timing still plays a reasonable role on the roads, right? Still, a lot of traffic signals are actually all of the traffic signals are on static preset timing. Okay, but every day we lose a lot of time on the road, right? A lot of inefficiencies because of that, because we don't feel it that way, right? So that's why we do not appreciate or criticize, right, having preset static timing. So it's not adaptable, right? As I explained to you, um, not adaptable to dynamic real-time changes. Of course not. It's not. It's blind. It cannot think, cannot see, right, what's happening on the road. So it simply repeatedly apply cycle after cycle after cycle the same timing, or according to the roster, the timing schedule, depending on the time of the day. So because this can actually become very, very inappropriate given the circumstances on the road, very different from your collected data in the past. It can actually lead to traffic jamming and all, right? So it creates congestion, slows down the flow, okay? Because it's inappropriate. I'm sure every one of us, every one of you, right, have experienced, right? How many times have you been waiting in the cross section, right, intersection, knowing that there are no vehicles on the other side, but still it is green and you are red, okay? These 5 6 seconds or 10 seconds could have been saved, okay? But just because it is preset timing, you can't do anything about it. And the other thing is that if you change this in an ad hoc manner, right, it's also very dangerous. Even though there are no vehicles, you quickly switch on the other lane and all that. So for a moment, you think, okay, it is good, so that the vehicles are now getting to move, right? But the thing is, you are disturbing the cycle. It's like a cycle, right? It's a synchronized process. Now, when you disturb it in the middle, right, here and there, after a few cycles, you will run into other problems. Okay, so therefore, you have to do it very carefully. So the problem statement, when the actual traffic pattern differs from the average traffic pattern, the signal timing is based on. So signal timing, like red, amber, green on one lane, the other lane, and all that, we call it phases. I think you know this certain junctions, they have 4 phases, sometimes 5, 6, 7. You can have different phases, right? This is how you allow vehicles to go, right? Straight or turn and all that, right? In one cycle, and then it repeats. So in one cycle, you can have 4 phases, 5, 6, whatever. The traffic control performance degrades. Now we know it pretty clearly. When this difference is so significant, right, when the actual scenario is very different from what you have collected over the past, right, then you have to call the police, right, traffic police to take over the control. You have seen this is happening in many areas, right? So then when the traffic police is in control, what he does is that he uses human vision, human image processing. He look at the road, how many vehicles are there, this way, that way, and he come up with some sort of control algorithm, right, using his intelligence. And then he controls timing. That's what the policeman is doing. So he is able to get things under control when the static timing fails. Now, if you want to bring in some sort of adaptive traffic control, I think you must follow the process of the traffic policeman, or maybe do it a little better than that. Okay, so let's think about how we can remove the person and duplicate or create the same function, right? He is doing. So therefore, I would suggest you use machine vision and image processing. These are two technical areas, very fast track areas in research and development, and also use some sort of artificial intelligence to interpret what you see, what the images have captured on the road, right? And try to figure out what the images are telling you, right? The traffic intensity, different types of vehicles, how bad is traffic in one direction versus the other directions, and uh, use your intelligence, right? And then not your intelligence, but machine intelligence, right? And then come up with some sort of control algorithm to portion the timing, right? So this is exactly what we are doing in adaptive traffic control. By the way, if you have any questions, please raise your hand or just unmute your mics and ask. Okay, so that way we can make this very interactive, very interesting. Some of your questions would actually be very helpful for the others also to actually polish or consolidate the knowledge on the field. So now what are the objectives of adaptive traffic control, right? Or adaptive traffic sensing. It is to develop technology for accurate traffic sensing. That is number one. You need to have technology developed to identify traffic or estimate traffic level, okay, in real time. Right? This is not an offline thing where you collect data, go home and put it into a computer and analyze. No. So this has to be real time, which means the moment you capture the image, there should be the traffic level, right, available to you within a second maybe, right? And then you control your timing. So we have to develop the technology for that. And also to eliminate inappropriate waiting time due to static signaling. So this is the application improvement we expect, right? You want to reduce unnecessary waiting time at the junctions, right? And improve the flow, means how many vehicles that you can allow to pass through the junction, right? That is average, improving average speed of vehicles. So this has a lot of good benefits, when you increase the average speed. By the way, first of all, you reduce the delay, waiting time, which will naturally help you increase the average speed of the vehicles. And it's good for the vehicles also, right? You reduce the fuel wastage and all the associated problems like environmental pollution, air pollution, etc. Okay, so this has multiple positive effects, right? If we can do something in this area. And also the technology available or we are going to develop, it should be very cost effective because you're thinking about not just few intersections, it's about entire country, at least in urban areas or suburban areas, okay, where there is some sort of traffic. If you go to remote areas, this may not be necessary because just there's no much traffic problems there, right? Not many vehicles, and even though you control it, you don't get a lot of improvement, right? And it's also good if the adaptive traffic control system can self-learn, right? Which means I think you guys have heard about artificial intelligence, right? It is somewhat pre-programmed thing. Okay, it is like fast food. Somebody has done it and make it available to you. Okay, so self-learning is another thing. You can have a AI entity which is not self-learning, right? But it has some sort of intelligence. It repeatedly use it. Okay, repeatedly use it. Like for example, Chat GPT, right? Chat GPT, which is running on the internet, is not self-learning as it runs. But there is another Chat GPT which is being developed, Chat GPT 4 maybe, right? So it is being developed in-house, right? Behind the screen. And when it comes to a certain level, the problems that you have in Chat GPT already solved in there, they will put it forward, right? And the Chat GPT will go out and it will be another GPT, right? So like that, intelligent systems can be non-learning or learning systems, right? So this is a fancy idea. Maybe in the far-fetched future, you have this adaptive traffic controller, right, that you connect into the junctions, and that's it. It doesn't have anything, just like a small kid, an infant, right, few days old, doesn't know anything, but look around and figure out what are the objects, how to deal with it, etc., etc. This device will self-learn how to handle traffic, right? So it will do some sort of experiments, and sometimes the experiments will not go in the right direction. There can be traffic jams and all that, but it quickly learns, right? And then in a month or two, it will do the job properly, right? So that will be very, very easy for implementation, because you don't have to learn the network before you put it in there. But the risk is, in the initial learning process, it might make bad mistakes. So therefore, there should be a compromise between the two, right? Fully pre-programmed adaptive traffic controller, or maybe programmed to a certain level halfway and then put it on the road for self-learning. Okay, so that way you can reduce that risk of initial problems. All right. So mind you, the biggest problem here is that every junction is unique. So when you use artificial intelligence, right, you do not customize it to any particular junction. You make it like more generic. Okay, so when you develop the AI entity, right, you stop the training at some level. You do not overtrain the network. Network means the AI engine, okay? Because if you overtrain it, it will be customized too much into that particular scenario. Maybe one junction, let's say Katubadi junction. If you overtrain adaptive traffic controller to Katubadi junction, you won't be able to use it at Piliandra junction or any other junction for that matter. It will only do deliver a certain performance, not the best. Okay, because it is too much trained into Katubadi. Because every junction is different. You need to train the network to a certain level without losing the generality, and then use it in other junctions and let it learn and customize to that particular junction. So if we can do that, we will have very live entity, adaptive traffic controller, right? Very much like a kid, a child, a brainy guy, you can bring it and embed it in every junction. And right on the day one, right from the get-go, it will handle all the traffic in a reasonable manner. But every minute, every moment, every day, it only improves. Okay, it improves to a certain level because of self-learning, and after that, it will operate in an optimal manner. Okay, so in the future, this is what the future holds, and I think we can actually be part of that development. So I'm actually not telling you the stuff from the internet. You can go to the internet and look around what is adaptive traffic control and all that. I want to share our own experience trying to do it here. So therefore, I think this would be very interesting for you, for that matter. Okay, these are our objectives, not only for the adaptive traffic control as it is now, but in the future, where we want to drive this field. So this is how you start if you want to do any adaptive traffic control, you want to collect data, okay? So use your cameras and also embedded platforms like Raspberry Pi that you can see over here, Palm Top computer, right? A lot of engineering projects are done on Raspberry Pi. Um, and it can actually, now this is just a camera, but this guy can use the images and process it, right? Image processing algorithms are run on this computer. This is a small single board computer, right? And the Raspberry Pi has its own camera. You can see it over here, right? This is a small camera of the Raspberry Pi. Then you don't need this camera, right? It can handle its own. Okay, so these are some of the images taken in 2018. This is Casbah Outer Circular Road, right? You can see the vehicles, lorries, three-wheelers, etc. Right? This is the first step in adaptive traffic control. Now, the second thing is you need to estimate traffic level, right, from the images. Well, there are multiple ways to do that. So I want to start with the least costly process here, edge detection, right? So this is one of the techniques in image processing to figure out the shapes of objects, edge detection, right? If I show you something, let's say this one, right? A multiply, okay? So if I take a photo and process it using OpenCV, right, on which is running on Raspberry Pi or on your computer, you take the image into the computer and process the edges, and you can see the shape of the object. Okay, so from this way, that way, like that, all like around it, you can take maybe some 30, 40 images, different angles, and you can see all of these things, right? And then Raspberry Pi knows once we tell, okay, this is a multiply, okay, and so it knows it. And once you train artificial neural network or deep network or convolution neural network, they are all different names for AI entities, trainable AI entities. All these photos are telling the same thing. It's the same object, multiply, right? So then if I show it a different multiply, I don't have one here, maybe somewhat similar to this one, not exactly this one, right? And take a photo and put it in there, and it will process it and tells this looks like a multiply, okay? And the correlation coefficient, the likelihood of this particular the new image being a multiply is 90%, like that. Okay, then we set a threshold. Any estimate above 90% we consider as 1, and anything less than 90 we consider as 0. So some threshold, and then we say we can conclude, okay, any other multiplier once you take it which is not significantly different to this one would probably be accurately identified by the trained neural network. Okay, So that is the typical process in machine learning. But what I'm going to tell you is something different that we have tested using edge detection. So there, we take the edges, right? Take the edges. We don't worry in traffic engineering, right? In this problem, um, what is this vehicle that we see on the images, right? Is it lorry or motorcycle, land vehicle, whatever, right? Let's go by edges. So we see the edges again, back to the same thing, right? Just one photograph and all the edges, and we count the edges, right? So when you have more vehicles in your image, obviously you have more edges. When you don't have so many vehicles in your image, you don't have so many edges also. So there's some relationship, right? You don't have to really try to figure out whether these are motorcycles, or vans, lorries, cars. Of course, in theory, it says the PCUs, right? The unit is calculated based on the size of the lorry and all that. But if you look at the images, the pixels also, edges, if a vehicle is big, it produces a lot of edges. If the vehicle is small, it doesn't produce a lot of edges. So therefore, this information is already embedded in the edges. So that is why we thought, why don't we try this first? Because it doesn't have a lot of computational complexities like identifying vehicles, right? We don't worry about the type of the vehicle, whether it is motorcycle or a lorry or whatever. We just went through edges, right? Okay, so we want to try it. So based on the features of image, we selected what is called the canny edge detection method. Sorry for this method, right? There are different edge detection algorithms like Sobel filters and Laplacian, but we figured out canny is the best. Right? It gives the highest accuracy in detecting edges in this sort of photographs, right? But if we think of something else, not the vehicles, probably Sobel or Laplacian would give you better result. But for traffic, vehicle identification, or actually not vehicle identification, edge detection of traffic photographs, Canny was the best. So we stick to Canny, and you can run Canny on OpenCV, right, on Raspberry Pi. So it's a small computer. You can like put it on roadside and power it up. So it's really handy in implementation. You don't need a computer to do the job, right? So there we first get the color images and transform into grayscale, and Canny detection applies on the images and identify the edges. Okay, so that's how it goes. Using the edges, we try to calculate the traffic level. So here you can see two photographs. The one on the left is the actual color image, and on the right is the edges. You can see a lot of edges, right? Objects and paintings and everything turns create edges. You can see not only vehicles, everything, right? So now you have to be very careful. We want to measure the edges coming from the vehicles, all right, not from anything else. Obviously, you can see the marks on the road. We should not count these one. These are not vehicle edges. Okay, these are noise basically. So what we do is we actually use a mask and produce only this part of the road as the near field, is the mid field, is the far field. This is basically the road. So all the other pixels are taken out. So that way we get rid of other pixels, right? Like that, the white ones, the edges. So it's only the road now. So when you do that, you can see how this image processing algorithms run, right? This is one of the objectives of the lecture today, to tell you how it happens in this technological area. Okay. So this is the near field. You can see these vehicles are captured, right? But in addition to that, these marks are also captured, and you get 5,322 pixels, right? and this is the near field, and this is the midfield. There also you can see these cars, right? They are generating edges, pixels, but also the road marks. This is the midfield, and this is the far field. The far field, you can see a part of this vehicle. I'm not sure what this is, and also road signs. Okay, so you are collecting all these edges, say mostly from vehicles in the near field, but when you go to mid and far, um, not many from the vehicles, right? It's from the road signs, road marks rather. So this is one of the problems. How do we get from the images to the traffic level, right? So here you can see another set of images, this one and this one. You can see a near field 4,000 pixels, midfield 2,200, and far 744. Right, in this one, you can see high number of vehicles in the near field, 4,700 almost. Right, so it represents the traffic level here, right? Increasing traffic level here, and this is 3,900, nearly 4,000 pixels, right? Because part of this one is actually captured, right, in the midfield. That is the problem. And this is the far 535. Okay, so there are anomalies here when you run this kind of algorithms, right? And of course, these things can be corrected if you position your cameras accordingly so that you high enough, you see the vehicles in the front area, right? Separately from the mid area and the far area, right? All what you need to do is to elevate the height of the camera, right? This way you can actually reduce this problem. Right. So I'm just trying to show you the small technical problems you might experience in doing this kind of research. Okay. But most of these technical problems can be actually resolved, right, by simple techniques. So when we look at these images and the pixel counts, it was our consensus, right, without any analysis, that this should work, right? Because you can see the vehicles, you can see the pixels, you can see they are related in a very reasonable manner. So you can see a lot of vehicles here, right? You can see 5,300. This is the highest number by far, right? Obviously, because a lot of vehicles, and 3,000 in the middle, 1,000 in the far field, right? So if we place the cameras in an appropriate manner, right, there's no occlusion of the midfield by the front field and so on, right? So this can only improve, right? So this is already good, but you can improve this. Now what we do is that you take a photograph and annotate it, which means you judge the traffic level of the photograph. Let's say for example, this one. When you look at it, I judge this is traffic level 3. Okay, so I define a scale, traffic level from 1 to 5, let's say. 5 means traffic jam, 1 means no traffic, and then all the other traffic levels in between, right? From 1 to 5. So take each and every image and annotate it. This is number 4. You can see this is little higher traffic, so I give it number 4. And this is kind of jam, nearly jam, right? So number 5, right? So this is very important. Look at these two photographs, right? This is smooth flowing. There's no traffic actually, no problem here. So I assign number 1, traffic level 1. This is traffic level 2, like that. This is extremely important. If you want to use any sort of machine learning, right? You need to let the machine know, right, what you mean by high, low, etc. Right? This is what is called annotation. Take the data set and annotate it, and that is what the machine learning is try to replicate. Okay, after learning, the learned entity will try to duplicate or replicate your judgment. Okay, right. So then we brought this annotated data set into MATLAB, right? And this is the photographs, right? Photograph 101 to, it goes on like that. And this is a near field, mid field, and far field, right? Pixel count. And we normalize it, right? To certain range. Now you can see 4 point and 5 point and this 6 point something, right? To a certain range, segment 1, segment 2, and segment 3, right? As you know, segment 3 is anyway small because it's far, right? Segment 1 it generates a lot of edges because it's close by, okay? But when you annotate the images, you actually, because you're human intelligence, you can actually look at this one, okay? How many vehicles are actually coming? You can see a lorry coming from here, right? So it generates 870 pixels. So you can give it a higher value, like 4. Not only you're looking to the vehicles that you see in the near field, but also you can judge how many vehicles are there in the mid field and far field, and then assign the traffic level. Your assignment, whether it is number 3 or 4, include not only the near field pixels, but mid and far. That's what I want to emphasize here. Okay, it's your judgment, human intelligence. Okay, once you do that, the neural network will look at it. Oh, this photograph has been annotated as high traffic level, right? But it doesn't have very high number of, say, uh, near field pixels, but it has significant number of mid field, right, pixels. So this traffic level being high is not only because of the pixels in the near field, but because of the pixels in the midfield and far field, right? So this complicated arrangement of the data eventually leading to final traffic level, right? The pattern is actually being remembered by the neural network. Okay, so that's the power of the artificial neural networks, convolution networks, right? Complicated patterns that we are unable to describe, right? Sometimes difficult to describe in a certain way. Of course, this one you can describe mathematically, but these patterns are automatically extracted by the networks, right? Artificial networks, and we call them machine learning techniques. Okay, right. So here you can see a set of images broken into near, mid, far sections, and then normalize the pixel counts in each section. And this is the human judgment. So this photograph we have judged as traffic level 1, and this is up to about traffic level 4, right? We don't have a traffic level 5 here because it's just part of the training data set. But if you look at the entire data set, there are all kinds of traffic levels are there. Number 1, number 2, number 3, number 4, and number 5. When you train, you have to give the network all different possibilities, right? So that it will learn everything, right? It's like when you raise a kid, you have to give the entire experience to him so that he knows everything. Anything that you haven't told him, right, not experienced, he'll not know what it is. Okay, right, like that. So then what about the think of it is same type of vehicles, only cars on that road. So problem is very easy, right? But now you have heterogeneous combination of vehicles, right? Especially motorcycles and three-wheelers. They are kind of different vehicles because they're very agile, right? They cut short. They sometimes go across the road, right? They turn like that. So it actually changes the dynamics of the traffic flow. They're not going one after the other, right? So how can we deal with this in machine learning? So when you, it's again human judgment. If you see a lot of motorcycles, let's say, maybe you should not give very high value for traffic. Let's say you see a lot of motorcycles in the near field. I would say this is not traffic level 5. I would say this is 3, because I know they're very agile vehicles. They quickly move, right? Not like big vehicles will take time to accelerate and turn and all that, right? So you can include that information in your annotation so that the network will learn it. So you get that point. So subtle uh, relationships that we know, but difficult to put it into mathematical formulas, can be transferred to the intelligence in the machine learning platforms that way, right? So it all depends on how you annotate each and every image in the training data set. So this is the workflow. Find the edges of the objects in the images and parallel processing and optimize the code. So when you do this one, right, on OpenCV, you can run this a couple of times and it will converge to a certain level so that all the training parameters are actually converged to that level. So after that, it's ready to go. So eventually we want to check accuracy. Now we are going to put a different set of photographs that the neural network has not seen before. And we ask, and they're not annotated either, right? So we ask the network to tell us what is the traffic level, as if you see this photograph, right? And we judge whether this is correct or not. Now, you can see here the algorithm, right? As I explained, first thing is you're capturing the images, right? And then you find edges in each and every image and the feed to the deep neural network, right? It is the trained one, right? Trained network, and it determines the traffic level of that photograph and show the traffic level, right? So this is what's happening once you have a trained neural network or convolution network. In the training process, it happens like this. You find edges in collected training data set, okay, feed to the deep neural network, train the deep neural network and save the network, right? So on a parallel process, you are training, right? So once you train it to a certain level, you put it into practice. So this part, this side of the algorithm is based on the training data. So you annotate and give it to the network and ask, please remember this, please remember this, please remember this. All of the images annotated and you feed it. And on the left-hand side over here, the images are not annotated. These are real-time images coming from the road, and immediately the trained network tells what the traffic level is. Okay. Now, this is the deep neural network configuration that we have used. It is 3, 10, 20, 10, 10, 5. This is the number of nodes in the layers. Okay. Right. Don't worry too much about that. Now, once you have a technique, right, basic technique, but it's working already, then you can keep improving. One of the problems we were having is the edges created by the road marks, say like these ones. Road marks create edges, right? When you apply the canny edge detection process, right? It detects the road marks as edges. So earlier we had another problem, but when your camera is not high enough, you will not be able to see near, mid, and far fields separately. Okay, that is another problem. These problems can be resolved by proper adjustments, right? Now let's talk about the marks on the road. So we have some decisions to make here, right? When we process the images, what if you process the image this way, right? So what you do is you take a photo like this of the road. Now, what is this photo? This photo doesn't have any any vehicles in it, right? We call it empty photograph. Let's say you can take an empty photograph of the road, right? So then you can see all of these signs here, right? All of these signs here. So when the vehicle comes in, some of these signs actually get occluded and you see the edges of the vehicle. But the thing is, when you show an image to uh, uh, the say tiny edge detector, it doesn't know whether there are vehicles there because you are not identifying vehicles. If you identify vehicles, it's a separate thing. Then the problem is over, right? You can just count vehicles. But here we do not identify vehicles. We go by the edges. So the easy fix is to get rid of these parasitic edges coming from the road signs, right? Road marks rather, not from the vehicles, is to have some sort of filtering like this. So what is it? You have the pixel color of the zero traffic image. So this is the zero traffic image on the left, right? It's a reference frame. So you use the pixel, any pixel in that image, right? So if it is white, which means a road mark, okay, sign, whatever mark on the road, white. And you check the same pixel on the other image, which is this one, right? Say somewhere over here, right? It is white on the left hand side image, and it is black on the right hand side image. So white becomes black. Okay. So like that, because it is now uploaded. So for the same pixel on the left figure and the right image. Okay. So if it is white, we don't count it. We don't count it because we don't know. We know white pixel can be an edge or it can be a road mark. On the left hand side, we know pretty sure this is a road mark. Okay, because it is white. It's a road mark. Okay, the road is supposed to be black, but if there are marks, they're white. So if the same pixel is still white on the other image, we don't know whether this is because of a vehicle edge or there's no vehicle. It is the same white mark on the road. So therefore, we don't count. Okay, there's a bit of a question mark here, but mostly it is accurate. And if white becomes black, again we don't count because black means not an edge. Edges are white. Okay, but if the pixel is now black, probably it is occluded by a vehicle. This road mark, this point is occluded by the vehicle, so it is black. So there's no need to count it anyway because black pixels we don't count. Okay. Now let's say there's a vehicle, there's a black pixel on the road, empty image. We know that it is the road. Now it is black on the other image. Again, we don't count because black means not an edge. But if the black pixel becomes white, we count it. Only in this situation we count. Okay. So this is a very simple technique to reduce the problem of these parasitic edge pixels, right, coming from the road marks. Now you can see it over here, the performance, if you apply this simple filter. On the left is the near field, an empty image, right? You can see a lot of road marks, like in white. Now this is when there are vehicles in the same near field. On the right is after removing the road marks from the image using the algorithm I just explained. So you can see a lot of pixels have already removed, but there is a little noise, which is anyway, any algorithm, right? You have a certain amount of inaccuracy. So this is perfectly all right. You can actually now see most of the overwhelming majority of the white pixels are actually coming from the vehicle. Clear? So these are the techniques we use in adaptive say identification of vehicles and traffic level, etc. Right? Just two techniques, right? Uh, so now once you corrected the pixel counts, you can get a very accurate set of edge pixels, right? Now you can see images are clean now. So then you train your network using a lot of images. Now we don't identify vehicles separately, but we use the pixels near, mid, and far field, and we eliminate the erroneous or noise edge pixels. Once you train the network with annotated set of images, then you put some test data set of images the network has not seen before and ask it to carry out, right, the process and then tell us what is the traffic level, right? Now here is some results. We put an image that we think of traffic level 5 and the network says 3.9, 3.9, which is actually when you round it up 4. The network says 4, then our judgment is 5. Then over here, we present a photo to the network, which we think of traffic level 4, and the network says 3.4, right? One shot. And what about this one? There's a photograph which we think of traffic level 3, and it says 2.88. Oh, pretty close. Actually correct, 100%. When you round this up, it will be 3. So perfect. What about this one? The photo of traffic level 2 and the network says 1.9. Spot on. So you can see over here, right, so many photographs, right, we have presented to the network and asked the network to tell us what do you think is the traffic level. And a lot of things, and only in these 4 that we have found some difference. Okay, and the difference is also just one, right? Just one, which means traffic level 5 is detected as 4, traffic level 4 is detected as 3, like that. So the network cannot go seriously wrong. It will not judge traffic level 5 as traffic level 2 or 3, right? The maximum error would be just one step up or down. And again, if you think of this problem as traffic level, and if you make a mistake of judging traffic level 4 as 5 or 5 as 4, it's not a serious problem, right? You are roughly around there, right? Maybe there's a little imperfection, but it's good enough. It's not seriously wrong, okay? So therefore, we can accommodate this kind of errors in this problem. It doesn't do a serious harm. So we can conclude that the validation accuracy is like 0.7 overall, okay? So the second thing is processing time. How much time does it take for the Raspberry Pi to actually, once it gets an image, to calculate the traffic level? So that's very important, right? The time. And we run it and we figure out start to end 7.6 seconds. It takes 7 seconds to process one image. And you can see few other cases I present over here. This one, 8 seconds, and this one is 8.5 seconds, right? Roughly around that. Our initial code base, right, without code refinement, code crunching and all that, it takes like 8 seconds to process one image, okay? So this is too much. Later, we refine the code and clean it up and speed up, and we were able to get it down under 1.5 seconds, right? 1.5 seconds for the entire process. So all these things are technically, um, um, we could handle it technically and improve the performance, right? Initially, it is 8 seconds, but we brought it down to 1.5 seconds. So when you have 1.5-second delay, it is real time in traffic, okay? Because anyway, when you put a green light, right, you don't turn it off in 1 second, right? You at least keep it for 5-6 seconds, right? Because vehicles start to move, they can't just stop, right? You have to let the vehicles pass a certain time. So if our decision can come within that time, minimum time, let's say 4 or 5 seconds, we can call it real time. So you can implement even this algorithm in real time. All what you need is Raspberry Pi camera and the software. That's it. And you need to get the Raspberry Pi to communicate to the PLC, which controls the traffic light, right? Then it is adaptive traffic control. So that's how you build a simple yet very effective adaptive traffic control. And if you look at the cost effectiveness, it is just a Raspberry Pi, right? If you look at just the component cost and all, right? All the other costs, I don't know, the labor, etc., right? We have to put it in there. But this is very, very cost effective means of developing an adaptive traffic control system. Yes. So that's the end of the first part of the lecture. Any questions about that? Any questions, or is everything clear?
So one question regarding the adaptive controls which you taught before. Now, can these adaptive controls communicate with, in a given junction, adaptive controls, can they communicate with other junctions as well? Are they working with integration fashion?
Yes. In fact, this is evolving technology is very complicated as well, and it is very you should do it very, very carefully, because it's like a ongoing thing, right? We don't have the luxury of freezing the time the traffic can actually do the experiments. So it's like you have to build the plane while flying, okay? So ideally, yes, we need to get the traffic of one junction and communicate to the nearby junctions. I think the traffic of one junction affects the traffic or dynamics of the other junctions when it is within, let's say, 500-meter area, okay, half a kilometer. So if you think of another junction 1 kilometer away, maybe 2 kilometers away, the effect of the dynamics of one junction, right, onto another junction 2 kilometers away is minimal, because there are so many other things in between, right, by roads, etc. But the best throughput, best performance could be enhanced, right, if you can communicate between junctions. That's for sure. But how we should do that is it has not been done anywhere else in the world, right? Only thing you know that in a straight roads like duplication road, for example, or goal road, some straight stretches, you can synchronize. But this is not actually what we think of as adaptive. This is just synchronization. Adaptive means you adapt your system based on the situation. So when you control your timing based on the real-time vision information in one junction, right? The outgoing vehicles, they are actually heading the next junction. We can communicate, okay, you can expect this sort of vehicles in the next 5 seconds or next 10 seconds. That information can be communicated to the next junction. So the next junction, right, it will receive information from the nearby junctions. This many vehicles are approaching my junction. After 5 seconds, 10 seconds, 15 seconds, so that it can actually be prepared for what is upcoming. Okay, so this is like evolving entity. So you can see a small cluster of intersections, maybe within 500-meter area, 5, 6 junctions, right? They are communicating to each other. And then there's no edge of that cluster, because these junctions are actually members of other clusters and other clusters. So it's like propagating model eventually, right? So we have had initial discussions with Professor Bandar, myself, and our team. Mathematically, this is very fascinating area now, right? How to get this communication from one junction to the neighboring junctions, right? And there are boundaryless clusters, right? Because so I'm a member of this cluster on my left. I'm a member of that cluster on my front. I'm a member of this cluster on my right, like that. So I'm a member of few clusters at the same time. Okay. So all the intersections are like that. So they are communicating around the junctions around them. So how you can build mathematics for that kind of thing? Certainly it is doable. Probably in the future, we will see highly connected junctions, right? Not just like synchronized one lane that we can see like in duplication, but very generic traffic propagation model, right, as a network of connected intersections. But that's, we have to wait and see. It's a bit too complicated, and trying out this kind of thing, nobody dares to try out this kind of thing, because you can easily mess around, and once you mess around, it's all over. You will not get a second chance in trying out that kind of thing. So that is a problem. So you have to simulate everything on Sumo and other traffic simulators. This is what we are going to do actually, and see how good you can make the system, right, the performance, if you communicate in that way. So again, I want to emphasize, whatever you see in duplication and other things, it's not actually adaptive controls. It is basically synchronizing. Of course, throughput is improving because you don't have to stop every junction, right? Once you pass one junction, you can get almost a free ride to some extent, right? So, but real performance could be enhanced or harnessed when you have a propagating model of traffic, right, from one junction. So if you have that kind of thing, then if you have a jam in one junction, that information will also propagate to the other nearby junctions, right? So their times will also be adaptable according to that, right? So it's like living entity now. Living entity, you know what living entities, right? So living entities are actually responsible entities, right? Look after things, are what is happening around us, and then they attend to it, right? So uh, but yeah, so this is something um, bit far-fetched. Any other questions?
So this study only aims for the vehicles, no, sir? So what about the pedestrians and all those things?
That we haven't considered here, because time given to pedestrians actually can be included as a constant thing out of the phases and all that, or can be included in one of these phases. It's a simple addition, because detecting humans and all is again very well established, right? We can incorporate that easily. And generally, so in our discussions, it turned out that the major part is basically vehicle driving. So how to control that and all. For pedestrians, you can leave that little time. And also it is like if somebody pushes the button, only you activate it, otherwise you let the vehicles go, right? And I think it's also not a good idea to have people on the road anyway. You better build overhead bridges for people to pass, right? Let's not get these things um share the same intersection space, right? So wherever possible, build the bridges or put a push button, temporarily stop. And also we thought of other things, like if there's a fire brigade ambulance coming in, right, we can easily identify it and then clear the road for that vehicle, right? So anyway, even though we don't do that, they will actually cross the junction. They will not stop. Yeah, these are the things in our concerns now.
So one more thing now, in this case, you use image processing.
Yeah.
Why not this CCTV or live videos are used to detect a number of vehicles and then, is it not possible?
Yes. Of course, yes. CCTV or Raspberry Pi, or you can use any camera, doesn't matter. Closed circuit images are also available. We can process using, say, canning edge detector on OpenCV. You can do the same thing. There's no difference at all. Yeah. Wherever CCTV is not available, you have to put this kind of device to capture images. Wherever CCTV is available, no need of cameras. We can just process the images and then control traffic. Just need some sort of imaging device, a camera, CCTV or otherwise. Any other questions, please? All right. Then we'll take a little break of 5 minutes, 8 minutes, right? And we'll start the second part of the lecture. Part recording. Okay, so part 2, mission-based traffic sensing. Right, now let me show you one junction. We were doing our experiments. The static timing of that junction, you can see it over here, right? The phase 1 vehicles are moving this way, and phase 2, phase 3, and phase 4. It's a 4-phase junction. In fact, this is that junction where one side is actually Piliandala Maharagama, and the other one is Caspav. This is Bokundra or something, right? Not Jaliagod, not very sure. So, and you can see the timing. This is the static timing, how static timing looks like, right? This particular junction on the outer circular road of Piliandala, 6:30 to 7 is phase 1, 20 minutes, right? It allows the main road to operate for 20 seconds rather. And then phase 2, 8, this one, phase 3, 15, and phase 4, 20, okay? And 7 to 7:30, it looks like this. And after that, till about 9, you don't change the timing, you use the same timing. And you change the timing again from 9 to 9:30, like you reduce 25 to 15, 10 to 8, 15 to 15, or don't change it, 25 to 15, like that. Okay. And then for the rest of the day, you maintain it. Now, obviously, this is not correct, right? You can't have the same timing that is 9 to 9:30 to continue for the rest of the day and expect best performance, right? And also, if you look at, say, 6:30 to 7, right, timing, you can't say that this is the right timing for all 7 days of the week, right? Because Saturday and Sunday are different from other days. Then there's no school traffic, right? So yet it's operating, and it gives you some sort of operation, right? Some sort of performance, and it doesn't lead to traffic jamming. So that is at least something to cheer, but also it doesn't give you the best performance. And the thing is, we never know what is the best performance because we have not looked at it. how much we are wasting in terms of time and other things, we do not know. We think it, we take it for granted and we see, okay, this is fine. But things could have been improved much more beyond what we normally see, right? So until we do a certain analysis and look at these numbers, we will never understand how far we could go, right, in terms of system efficiency and performance. Okay. So this is something I have already explained to you, so I just skip that part. So this is how adaptive traffic control operates on a certain junction. So it's a four-way junction. You have traffic timing, red, yellow, and green, all these four lanes, okay? And I mean, there are 3 lanes in one direction. And you put cameras, of course, as somebody said, if you already have CCTV, we can use those images and process, right, and control timing. And if you can see over here, there's some electronics running in one of the junctions, right? This is where all this information is collected. All videos or images are collected and processed and take decisions, right? There are, so when you implement this kind of thing electronically, there are various ways to do that. You can have a processing element here next to the camera, all 4 cameras, they process and then come up with some sort of traffic level analysis and then communicate that information to the central device, okay? That is also possible, but what we did was we actually connected all 4 cameras into one place where the processing takes place, all 4 video feeds, okay? So if you process at the edge here, we call it edge processing. So you need to have some sort of electronic device, single board computer to process images. So if you have one edge processor here, another one here, another one here, you need to have 4 of them. But what we did was we got one single edge processor to process all these things. And this is the camera view. So you get something like this. Now you can see the, if you compare with the previous thing that we discussed before the break, the near field, midfield, and far field. If you want to use that technique here, you can clearly see the areas can be separated without much of interference. Still, there is a little bit of interference because when we mark the near field, midfield, and far, it's a straight line, but the vehicles are not straight lines, right? So they share partly here, partly there, and so on. So there's occlusion therefore. So, but the problem can be seriously remedied this way by just by placing the camera the right angle and right height, okay? And as I said, they are wired and they are connected to one single junction where the PLC is located, signal control is located, right? So even though the signal controls are located, distributed around the junction, the controller is just one and it is somewhere here, right? Then you have underground cabling to connect these PLCs and then you can control these lights. So our new unit, adaptive traffic controller, is going to be next to the PLC control board, the small white box you can see in junctions. This is where the PLC is, right? And time to time, SDNCC, the company who is actually subcontracted by the Road Development Authority to control or set the timing and all that. The technicians of SDNCC, they come and open the white box over here and they change timing if they want, right? They program the PLC. So if you run without any adaptive traffic control with the static timing, right? because the vehicle dynamics change. I mean, new vehicles are coming in to the roads, right? Every few months, you need to collect data and look at the latest situation. Dynamics have already changed, and accordingly update the static timing. Even the static timing should be updated. And unfortunately, even that is not happening in Sri Lanka in a effective manner. So therefore, most of the roads, intersections, I mean, are running obsolete timing, right? So now we have two problems. Not only the static timing is inappropriate and far from being optimal by any means, right? And on top of that, we have the second problem. The timing are based on past data, right, which is it doesn't have any meaning today, right? So this new technique is different or advanced compared with the previous technique based on edge detection. And this one actually detect objects, not the edges, but the objects, vehicles, right? There are different types of vehicles. So this is much more complicated convolution neural network, right? It is trained to detect vehicles, right? So it goes through this convolution network of object detection and then object tracking. Once you detect, you have to track it. Okay, you have to track it. Why? Because you need to figure out whether the vehicle is coming in this lane or crossing to the other lane, whether it is trying to go straight or whether it is trying to take the turn. And also, you want to track the vehicle to measure the velocity, okay, speed. You take the vehicle, capture it, and identify it one image. And after, say, half a second, you identify the same vehicle on a different frame, and you know the distance traveled and time it took, right? Then you can calculate the average speed. So that is how we calculate the speed without using any radar sensors or anything, right? Uh, so then we get the flow information, and then eventually we can connect it to the green time, right? So this is what is called the standard state-of-the-art adaptive traffic control. So what I explained earlier before the break is not the state-of-the-art. It is far less technical, right, in terms of the technology that is in the product, okay? But here it's not a fancy hardware or technology that we need. We need something to solve the problem, right? Whether it is high end or low end, it doesn't matter. As far as it is reliable, sustainable, and cost effective and does the job, that's all what we need. So therefore, I would suggest this kind of fancy and also very accurate, right? Vehicle identification, tracking, and velocity measurements, are all these things, right? Is expensive, and it should be at places where it is extremely absolutely necessary. But all the other junctions, you don't have money to invest on all the junctions, right? Because this is expensive. For that, maybe the previous technique based on edge detection could be a very good alternative. So here, this I show you for the completion on the left, but you see the convolution neural network. Don't worry too much about it, but remember the name, right? If you want to identify objects, right, you might need a convolution neural network, right? Say an apple, you want to differentiate apple from mangoes and from oranges, right? You show the photographs, right, of apples or different types of apples, right? Various photos from the front, left, side, top, and all, right? And tell that these are all apples, right? So it's a group, a class of apples. And then again do it for oranges, right? Different types of oranges, right? Big, small, and whatever. And the network will look at it, right? And then separate it out, two clusters. So like that, vehicles can be identified by the convolution neural network once you train it. But if you want to train a neural network to identify vehicles, you need a large number of photographs, right? Say car, the different types of cars, right? Different types, different shapes, sizes, etc. So you need to collect all these photographs, not just one type of cars, right? All of the cars, right? From Toyota, from Honda, from Nissan, right? And then take the photos on different angles, from the top, front, at an angle, and then feed those photographs, maybe hundreds of photographs, right, of the car class. And similarly, motorcycles, three-wheelers, lorries, light vans, Bowsers, land vehicles, landmaster, things like that. All of these vehicles, and then train the network. Once you train it, you can identify. The network can, when you present a photograph, can identify which type of vehicle is this, right? And vehicles are identified by the network, and it put a bounding box around it. If you see the vehicle in the image, it will create a box around it. And in successive images, you can identify the same box, okay? And then this is how you track it from frame to frame, right? You bring this rectangular or square shape bounding box of the vehicle. The vehicle is inside, right? You will see this in future images, graphics, and videos. You know the time between consecutive frames, and you can easily calculate the average speed. So that's how it happens. So we have had 20,000 annotated images. This is one of the downsides of these machine learning techniques, right? You need a lot of data to train a network. So 20,000 images, right? We had a really bad time. Actually, we hired many students, interns to do just the annotation, because it's a very tedious job. You have to just sit right on the computer and take one by one and annotate it, right? It takes a lot of time. So there you can see this annotation, right? You can look at these photographs and see this is a van, this is a three-wheeler, and so on. So once you do that, the system is, once you train it, it will identify the vehicles accurately. You can see this one, three-wheeler. This is the accuracy 0.88. This is a car 0.9, 90% accurate. So you can get that accuracy also, right? So they're all above a reasonable doubt, okay? So in the range of at least 80s and mostly 90s, I guess, right? Yeah. So this kind of accuracy is actually adequate, right, for traffic controls. And if you look at the problem, you would say, what about night? The traffic problem is not only during the day, right? Even nighttime it's there. But the problem is, the reality is, it's not as tense as daytime, right? Of course, when it gets to 6:37, 8, yeah, so the problem is there. It actually eats into the night or late evening, right? So we need to have recent accuracy at night. So once we tested it, we got these results. So the system is able to identify, because there's light, right? Sometimes when the sun is not there, probably it helps you to identify the vehicles, right? So the light is important here, right? All these vehicles, we need to see the vehicle shape. But night, because of the illumination from the surrounding and the lights of the vehicles themselves, right, is adequate to do the classification, right? So all of the data we annotated are actually daytime data, right? But when you try it for nighttime data, it just worked. So if you trained the network with some nighttime data, right, and we would have gotten a differently trained network, right? This is certainly doable to improve the accuracy. We collect a nighttime data set and annotate the vehicles, right, and then train it. And when the light level drops by a certain threshold, we change the neural network to the nighttime neural network, and it will do the job. So these are all different techniques we could test in adaptive traffic sensing and adaptive traffic control. And this is actually able to detect motorcycles also. Can you see that? This motorcycle is partly occluded, but the network is much more sophisticated than you would think, right? It can actually detect those motorcycles. There is another motorcycle here, but for some reason it is not detected, right? It is not detected. These are some other photographs. Interestingly, there is a car here. Even I can't see it, right? I don't know whether you can see it. In fact, there is a car here, right? The students confirm there's a car by when you enhance. So that is actually detected by the machine learning technique. Everything is clearly detected. So it is much more accurate than you would think. Somebody said about pedestrians. So actually, I don't think this is a pedestrian being detected, maybe something else, motorcycle or something. I don't know, right? But there are other ways now. Human detection is very easy compared with vehicles, right? You have a shape and all that doesn't change much, right? So we can incorporate to identify people. Now, yeah, so how do we incorporate human imagery in adaptive traffic control for various reasons? Maybe as a safety measure, if we see people on the road, right, and we can immediately change the lighting to red or whatever. So just the possibility. I'm not telling that we should do that, but some workaround is certainly possible. If somebody finds right in the middle of the road when he's not supposed to be there, right, the system can actually intervene in some way, right? Again, some out of the box thinking. So entire adaptive traffic control system as a block diagram can be represented like this. Yeah, for a four-way junction, right? You have four cameras, and then they're all getting the video feeds to the power on the Ethernet network switch. Uh, then our main processor board is NVIDIA Jetson Nano, which is fast enough, capable enough to process all these images, right, in less than a second, right? All four video streams. This is not Raspberry Pi. This is much more advanced, right? And it'll run the convolution neural network and identify vehicles of all these four streams, and it runs a certain timing algorithm, okay, how the timing should be adjusted. So earlier I showed you static timing table. Now this board, after going through the four streams of video, right, evaluate the traffic levels and adjust the static timing. It will not stick to the static timing at this moment of time. It will adjust it slightly. Now, when you do the adjustment, right, it's better if you keep the same cycle time initially, right? So it may be 150 second cycle time. So 150 seconds divided into four areas, four phases, if it is four-phase thing, right? But altogether it is 150 seconds. And the next cycle is also 150 seconds. So you're not going to change 150, but you're going to take few seconds from this phase and put it into the other phase and all, right? So this is internal adjustment, but we keep the 150 seconds, right, intact. Because you need to solve one problem at a time and then go to the other. So we can't change many things at once, and so therefore we cannot judge what's happening, right? If you look at the outcome, we should be able to relate it to what we did, right? So when we have too many things changed, it's a bit complicated. So now what about the cycle time? Cycle time, is it the optimal cycle time? I don't think so. But unless we have a certain way to calculate what is the optimal cycle time, we should not change it at this moment. So you keep the cycle time unchanged and do the adaptive timing within the cycle time. So phase times are adjusted, not the cycle time. But when you look at the broad picture, looking at the nearby junctions, right, you can set a cycle time, most appropriate cycle time for the junction. Right, so all in all, the timing is adjusted over here, and the new timing is sent to the PLC, program logic controller, which will actually display the lights, right, accordingly. And at the same time, the data is actually sent through a 4G router to a cloud base. So in the cloud, all this information is recorded, right, for the later analysis, all right? So this is the architecture of a adaptive traffic control system. And if you look at the software side, for your information, it goes like that. Don't worry too much about it, right? So once you set up your LAN and receive camera streams, you pre-process them and buffer it and send it to vehicle identification detection. And then you do the tracking. You keep that information and see where the vehicle is in the successive images, and you do the flow calculation, okay, lane change, etc. So that's software flow. Right. So we did some simulation on Sumo, and also in fact, in Sumo, it's difficult to adjust timing directly. So we had to improve Sumo so that we can actually implement adaptive traffic control on Sumo, right? So it's originally a simulator, but not a control platform. So we improved it a little bit so that we can do the timing and then put back on the simulator and see how it happens, right? So this is the junction we did the simulation on. We got the data collected from the images, set of images, and we set the static timing accordingly. Then we ran the algorithm on Python, and then just the timing. So let me show you the simulation result. Before that, I want to tell you how the adaptive timing takes place in this little example. So if you look at this junction, this is phase 1. You can see it over here, phase 1, 2, 3, 4. Let's say we have a static timing 18, 18, 18, 18. So it's 18 seconds for all 4 phases. Just an example, okay? So the total, this is actually green time, okay? Green time, constant 18-second green time. So total green time is 72 and minimum green time is 10, right? You cannot reduce this below 10 seconds, right? I think you know all these things. So here you can see some sort of equation. Don't worry too much about it. The equation again, it is actually adjusted time based on the real-time traffic information. Okay. So this is phase one. The vehicles are moving straight and turn to the right along this lane, right? And this is phase two. Again, same as phase one, goes like that. And then you have the two lanes going straight, opposite lanes, right? Three, and this is phase four. Okay, turning. That's it. So now, if you get the real-time information, say for example, in phase one, right? This is phase one. 20 vehicles are there to go straight, and five vehicles to turn to right. So it's altogether 25 vehicles. Okay, in this phase. And phase two, I think it's over here, 17 vehicles to go straight and 7 vehicles to turn right. So it's again, how many? 24 vehicles in phase two. Phase three is, I think, these two straight arrows. So it is 10 and 6, 16 vehicles in phase three. And finally, phase four is the 7 vehicles to turn right and these 4 vehicles to turn right. So it is again, how many? 11 vehicles. Okay, so these are the actual real-time information, So we just put it in here, 25 phase one, 24 vehicles phase two, 16 vehicles phase three, 11 vehicles phase four, right? If you just count the number of vehicles, but you might say counting vehicles is not very accurate because there can be small vehicles, there can be, oh yeah, that is something very easy. So you use PCUs, right, for large vehicles and small vehicles and get the number. That's a simple arithmetic. You can do that. Okay. Once you identify vehicles, right, everything else is simple. And then you run some sort of algorithm, right? The principle is that you give little more time to where you have the most number of vehicles. Okay, by taking little time from where there aren't many vehicles, right? Of course, you can see this 18 is not good enough. It's actually too long of a time for 11 vehicles, whereas this 18 is too short of a time for 25 vehicles. So definitely you have to take some time from this 18 and put it back here if you want to keep the same cycle time, but adjust within the cycle. This is exactly what we do, right? There's no magic here. So once you run this algorithm, you can come up with some sort of algorithm. I don't really advocate anything here, right? So using this kind of algorithm, you can actually say, we'll set 18 to 20 seconds, this 18 to 19 seconds, and this 18 to 17 seconds, this 18 to 14 seconds. You can see the new adjustment, right? We only give 14 or 15 seconds to phase four, but we increase phase one to 20 seconds, right? But you are not changing the cycle time. So therefore, you are not actually messing around. You are not taking unnecessary risk here because you are contained within the cycle, right? So nobody else will see what's happening within the cycle time, let's say, right? All the other nearby junctions, right? You are synced with them, say 72 green time, and there are other times also. If you combine all things, is cycle time. It's not going to change. All right. So there are gaps probably if the pedestrians are there, a little time, but overall, it can be 72 plus of some seconds, right? Yeah. So this is how the system is developed step by step. So the last column is actually once you round it up to seconds, you don't want to go below 1 second, let's say, say 500 milliseconds or whatever, half a second, right? Because you're dealing with vehicles, right? So anyway, they're a little slow to start and stop and all that. So therefore, in terms of seconds, we measure everything. This is the simulation on Sumo, which is actually not only simulation of the vehicle flow, but also control traffic. Okay. Now you can see some graphs over here. And the static flow in blue here, this is the dynamic flow. When you adjust timing based on your traffic, right, you get it like that. What is this line over here? This flow, right? Flow, right? So how many vehicles you pass in that junction? And here, this is green time variation. In seconds, you saw a little example earlier, right? The blue one is phase one. This is phase two, phase three, and phase four. You can see the changing dynamically, right? Every cycle is a different phase time. So in this simulation, we were able to send 100 to 300 more vehicles per hour, right? So 3 to 5 seconds or less delay per vehicle at the junction. Stabilizes green times proportional to the traffic flow. Right. So to do that, the whole thing, we need to improve Sumo using a Python patch on top of that, right? So what the Python code is doing, because this is you're running Sumo on your laptop, right? And it has all the vehicle flows and all that, the junction parameters, everything. And you run your Python code on PyCharm as a project, and Python code communicates to the Sumo, right? In terms of dynamic signal timing, it tells Sumo to adjust timing, and then Sumo gets all this information back to Python. So the physical implementation is next thing. We were yet to do that because of the practical problems, because we don't own roads. There are owners for the roads, and we want to go begging for various things, and it's hard to come by. People, there are supportive people for this kind of R&D, but there are a lot of people who are not actually supporting this kind of thing. They are happy with the way it is. Whatever inefficient system is their lifeline. So this is why Sri Lanka is unable to develop for decades, right? I don't think we will ever be able to develop with this mindset. Lack of interest for new technology, and a lot of red tapes, a lot of rules. And even if you get approval to do something on the road, you get it after trying for a few months, and you get the approval for a few months. And the moment you try to do that work again, after 3 months, your approval is expired. You have to spend another 3 months for the extension. So it's not worth it involving in this kind of research if the system does not support, right? So we'll stick mostly on Sumo-based Python, and we see the whole traffic improvement on the computer, not on the real ground. Right. The last thing I want to discuss with you is traffic analysis tool. This is a separate thing. This is not adaptive traffic control. Some tools that is helpful for RTA, for other people, researchers, to analyze the traffic videos and get the numbers, right? Vehicle dynamics. So what the problem we are trying to solve here, we need to periodically measure traffic parameters, velocity count, etc. for junctions, right? Let's say you stick to static timing. There also you need to upgrade the static timing periodically, right? So not to make it obsolete, right? Even though it is not the very accurate thing to do, right? But at least something. But that is to be updated periodically every 3 months or every 6 months, or sometimes based on how fast the dynamics change, okay, in that locality. And this is extremely important for adaptive traffic control as well, because as you probably would have understood earlier, the adaptive traffic control sits on the static time, right? The cycle time is coming from the static timing, and then you adjust in between, right? Inside the timing, cycle time rather. So after that, maybe you can try to change uh, uh, the cycle time. That is open problem, right? We don't know yet, because we haven't mathematically modeled it, we haven't simulated it, we haven't seen elsewhere the cycle time change adaptively and what's going to happen, right? I'm not very well aware of that. uh, I don't think somebody has done it to the perfection, right? Anyway, so static timing is very important to be if it is updated. Otherwise, it's useless again, right? Now there's a question here. Have you tried during bad weather? Yeah, there are some photos taken during rain and all that, right? And there's a certain maybe 2-3% drop in accuracy in bad weather. And we actually we simulated the weather in the images. We just put another mask kind of thing to show the rain and all. And it was able to detect vehicles. And but with the drop of a few percent accuracy. But if it is raining at night and all, again, not very sure, not very sure. Now, this traffic analysis is usually manually done. You have people, maybe some of you have been involved in this kind of surveys, right? You go out there with with a with a chart, and you sit on the roadside couple of hours and fill the form, right? How many vehicles, motorcycles, cars, etc., right? And that is your traffic data that you collect. And based on that, you set the static timing, right? There are standard algorithms to do that. Now, this kind of work, tedious manual work, now should go away. Now, technology is much more developed. You can do it automatically, right? So what we thought of developing is that these are not very novel techniques, though. You just get a video camera and put it on the road and collect the video and upload it to the service, which takes your video and then analyze. Of course, the service cannot analyze it for you entirely because it doesn't know what you want. So therefore, you have to do some sort of initial setting off, right? What you want to measure, what you want to count, straight vehicles or turning vehicles or whatever, and whether you want to calculate the speed also, right? So this platform was built so that you can upload your videos and get the analysis, right? So this analysis will get you 18 different classes of vehicles, right? I'm not very sure whether all 18 were trained for, right? And it gives you speed of the vehicles, right? Turning and all, density, time headway, space headway, cube length, waiting time, everything, right? Once you have the images, right, and you track the vehicle in consecutive frames, you can actually calculate all these things. There are two modes. You can do this on. One is you get a video and upload it. Second one, you have a device. So there's a device already built. It's like a small robot. You just put it on the road. It collects all the data and process everything, right? And it runs the whole thing right? Runs the whole thing and give you the result. There's no cloud there, right? You don't have to submit anything to the cloud. The device will give you the same data, okay? And we have found the vehicle identification is 100% at daytime. It's 100% accurate, 90% plus at night. So there's some sort of degradation at night. So I'll show you that video in a while. And here you can see a concept here. This traffic analysis, what you do is you have the junction, right? And you mark the lines, right? You can see here, blue line and yellow one. So like 10-meter apart, 10-meter apart, okay? You draw it. So, so this counts all vehicles that enter downward through blue line and leave leftward through red. So all the vehicles we are turning like that and goes this way are counted, okay? So this is one requirement, your requirement. You draw it, blue and red, then system knows, okay, you want to count this vehicle. And speed is also measured. And there's another line over here, another blue one. And it says counts all vehicles that enter leftward through blue line and leave upward through the red line. So maybe enters here and then turn like that. So you can draw these lines the way you want and ask the tool to analyze the video. So this is a video of that service traffic analysis tool. You can see these lines, right? From here to here is about 10 meters. So you measure the speed of the vehicle. And this is tracking. You can see these lines, vehicle tracking, and it exit over here. You count it, okay? So you measure the velocity here and you count as it exits from here. This is another one where you can see vehicle motion and tracking. It's a bit of noisy sometimes, right? You can see it over here, but it's accurate enough. You can see the lorry turning towards you. It is being tracked. Okay, right. At night, it looks like this, and some vehicles are actually missing because it depends on the location, right? If you have strong street lighting and vehicles can be seen, accuracy improves, right? So these are the different types of vehicles. Almost everything is taken, included, right, in the system. So this is a little summary of manual counting the vehicles, which we think as most accurate, right? And then you ask system to do it and you get 99%, 98 or 91% at night time. Missed vehicles, double count. You can see the double counting is very small, right? 1%, 2% like that. The non-vehicles being identified as vehicles at night is 2%. During daytime, 7%, because a lot of vehicles, right? And there are objects, not moving vehicles, but stop sideways are also being detected sometimes. They're not moving, right? So system is not perfect to identify this is a stationary vehicle, so that should not be counted. So incorrect classes is 2%, which is a motorcycle being detected as a three-wheeler or three-wheeler detected as a car, like that. And nighttime is very high, 25%. Right? Obviously, you can't see the whole vehicle, but part of that. With that, it measures, right? So maybe you can see only the front side, and it doesn't know whether it is a car or a van, right? So if you cannot see the whole thing, you have to expect this sort of errors. But now again, as I said, all these imperfections, there is a cure for that. Very simple cure for this one. You don't have to worry too much about developing the algorithms or whatever. Just shine some light on the road, right? Because this is one single place on the road, right? you put some lighting in that area. That's good enough. That will improve this performance. So 25% can be brought down to 5% just by putting some light. Okay. Or you change the camera, you use the IR camera, which can see at night. Okay. So this way you can easily get rid of the problem. So once you do that, either using this device, sorry, I don't have that image of the roadside thing. We are still building it, but I would have showed you a photo or image. I just want, it's in my computer. I just don't want to spend time to find it out and present. So if you have the roadside device, you get that data directly using a flash drive. Or if you use the web-based online platform, you just upload the video and generate the CSV file with all this information. So using that, the authorities can actually update the timing, right, in junctions. So we have proposed already to RDA to have some sort of remote communication with the junctions. This can be easily done, right, through a communication module attached to the PLC, programmable PLC, and you can program it from here, from RDA, right? You set the new timing. But to do that, you need to have this information. So you can actually use, let's say, Google if you want. There, if you would use the Google development platform, you can actually don't need this kind of device. But it depends on what sort of accuracy you are thinking, right? The Google actually does not detect vehicles, right? It detects the mobile phone, right? So say, let's say, if there's a vehicle and there are a lot of people there and they are having mobile phones, they're all being tracked. So therefore, you have to be careful when you use Google data, right? And also, if you don't have a mobile phone and somebody's driving a vehicle, it's not detected, right? It's because Google is not actually detecting vehicles. It is detecting the phones, right? Location devices. Yeah. So it's important that you have the remote programmable PLCs, right? There's a certain improvement surely doable so that you can have these devices or at least take videos and process them. And once you process them, you can actually put it in the timing algorithm and update the time. You can do the whole thing right from RDA. I know RDA has maybe 1 or 2 people to go out there, RDA, OST, and CC. I'm not very sure. I heard only 1 or 2 people to cover the entire country. My God, they're not going to do this life, right? How can you do that? So most of the timing intersections are actually obsolete already, not recent times, maybe years ago. So therefore, you cannot expect performance even with the static timing what you're supposed to get. Okay, not to mention about other imperfections in the static timing. Right. So this is a little graphics on this roadside device, just a camera and some processing device here, some battery support, etc. You can process everything and get your data out to a USB stick. Yeah, right. So I just want to say thank you to some of my students, 4 students who did this project some time back, a couple of years ago. And there are a few other people who contributed, they are not here. Right. Yes, that's about it. Any questions, please?
Sir, that you told about the Google data, like can
Yeah.
you actually get the velocity, speed, and those things that you detect from the camera and the wavelength and everything through the Google data only?
No. You have to like we did in case of Sumo, took the Sumo and we wrap around Sumo a different algorithm, right? Like in Python. Same here. I think I haven't done it, but if you look at the Google data, you can get some idea, and you have to do the rest around it. Yeah.
Okay.
So, like Google Earth provides you some sort of platform, right? I think it's not free. You have to subscribe to that, and then they allow the platform for you to do whatever research on it. I think Google also might have that kind of platform to get the traffic data. And if you talk to Professor Bandara and Dr. Dimantha, Dr. Dimantha has done it some time ago, right? With Google data. So, but they have just taken Google data and without doing any wrapping around it, right? Just raw data and then did the analysis. That's all. But if you want to do something like I showed you here, static timing, upgrading, and you want to actually calculate the latest situation, then of course you have to do a wrapping around that Google data.
Okay. Thanks.
You're welcome. Any other questions, please? All right then.